Yeah, Jacob, if you want to take it away, you can.
Yeah, sure. All right, everyone, thank you for coming. We have a pretty good showing tonight, so that's nice to see. So really the point of this interest meeting is to just introduce you guys to the club, what we've done and like what we're currently working on. And you can kind of see like we have different subgroups, so you can see what you're most interested in. Next slide. So this is our executive branch. Alex, why don't you introduce yourself?
Hello, guys. I'm Alex. I'm a senior in biomedical engineering, and I'm the president of this club. I've been part of the team since like 2018, but only recently have we actually grown into like a fairly large club, recruiting actively. So it's a good time to join.
And I'm Jacob. I'm the vice president, and I joined last year. And Jason, do you want to introduce yourself too, since you're here?
Sure. I'm Jason. I'm the secretary. I basically just make all the TikToks, amongst other things.
He does plenty of other things. But
yeah, and then we have our treasurer is Michael. So he's actually in graduate school. He's doing his master's in electrical engineering, and he did BME undergrad. And Jason is actually from UNC, so we have a few members from UNC. You can go to the next slide. Okay, so we partnered with a few BME faculty who have been very generous with donating time to us. So they've given us personalized lectures, explanations of their research, and just helping us brainstorm potential ideas. So the first one is Dr. Helen Huang. So she's the director of the Neuromuscular Rehabilitation Engineering Lab. So that's NREL, I think it's pronounced. So she works on hands, exoskeletons, and legs. That leg you see in the top right is actually one of the legs that they designed that we got to kind of see firsthand. And the leg operates similarly to our end goal design. So we met with the lab last semester. We got to see the leg and different control systems that they use. Unfortunately, we don't have, I mean, we do, but we don't want to spend $7,000 on control equipment. So we can't use exactly what they're using, but it gave us like a good starting point. And then we have Dr. Sharma. He teaches biomed mechanics, and he researches nonlinear controls. And we had a lecture with him on nonlinear controls last semester. We learned a lot during that. And then Dr. Bruce Wiggin and Dr. Camper are also involved with our club, mainly like advising and stuff.
yeah, Dr. Wiggin also does a lot of mechanical design work and manufacturing related stuff. So he's like our main point of contact for when we want to get things manufactured and sort of any design advice for that as well.
All right, so motivation for us is, so there's a sizable population of lower limb amputees in the US, certainly more than I would have thought. And obviously reduced mobility greatly affects a person's day-to-day life. So that's really our primary motivation with this club. So here's kind of the evolution of prosthetic legs over the years. So you start with your peg legs, really simple designs, and then you get into these mechanically actuated legs that work off of gravity and stuff. And finally, like at the end, we have these more modern examples. And a lot of these modern examples are trying to employ ways to actively predict knee angle and controls. So recent advancements in electronics have allowed for powered prosthetic systems, and these improve gait quality greatly. And that's what we're focused on at Pack Bionics because there's just a lot of potential there. And our goal is to design a state-of-the-art leg to help progress the field. Yep. Next slide. So our main goal is to compete in Cybathlon, which is a competition that occurs every 4 years. And it occurs in Switzerland, so that's pretty cool. And it's basically kind of like a little mini Olympics for prosthetics and rehabilitation technologies. So you have a pilot, we call it, who's an amputee who wears the leg, and they compete in this obstacle course that you can see here. And they basically just have to accomplish like day-to-day, like regular tasks. But as you can see, like it varies greatly across the length of it. So you have to walk upstairs, you have to balance. So that's really what becomes like the major difficulties is allowing for an amputee to seamlessly switch through each of these different states and be able to complete the entire course.
Yeah, so this is just a video from a few years ago of Cybathlon. I think it's actually changed quite a bit for this upcoming competition, but I still need to look at that too. So, but that's 4 years out, or a couple years out.
It's like 2 years out now.
Yeah.
The next one's in 2024.
All right, can you guys hear the video at all? Or do I need to share audio? Can you guys hear it? Or
no?
No. Okay.
I don't know how important the audio is though.
Is the video clear at least, or is it stuttering?
It's stuttering a little bit, but
okay.
Maybe. I think they get the idea though.
Okay. Well, I'll just play the rest of this video. Yeah.
Yeah, so that was from 2020, which that ended up getting canceled, right? I assume. I think.
No. So it went online.
Or it wasn't. Yeah.
Yeah, but like the whole logistics of it was like a whole mess. So
yeah.
We ended up not competing for that competition. And then also like we're like a very new team, and our design had some flaws that were kind of overlooked that were very detrimental. I'll just leave it at that. But yeah, so I mean, I'll talk about our team's past. So we actually founded late 2017 for the purpose of the 2020 Cybathlon competition. It was just a group of students with very loose guidance from various professors, but we were pretty much on our own. And so our first design you can sort of see here on the right was a dual cam cable driven system. So the two cams are up here and then this one down here. And then with a passive spring element in the back, and actively driven by a motor as well. But like we said, due to the pandemic, there were a lot of logistical issues with travel and sort of setting up the obstacle course locally. On top of the design flaws of our system, having to sort of deal with all of that was a bit much for our relatively small team of like around 10 people. But yeah. So yeah, this was an entire process for us. It was a great learning experience. I definitely learned a lot about mechanical design and mechanical design for manufacturing purposes, as well as the basics of PCB design and even software. So here's just a video of just assembling that first prototype. So this is something you might be able to do if you join the club. We're working on another iteration of the mechanical design, completely different mechanism that I'll talk about in a sec. So I think this is like a really prime time to join for gaining those experiences. But yeah. So like I said before, the present goals are to redesign the leg, implement an entirely new control systems, and then recruit and train a team, hopefully larger than the last, so that work can be more distributed. And yeah. So we'll give an overview of like some of the different areas that we're working on. So the first one is mechanical. So we're actually moving away from that dual cam cable driven system. There's a lot of potential issues that can occur with cable driven systems. And then on top of that, the way that we had those cams made the control systems very complex because they were not regular curves. And so we're actually going after a 4-bar mechanism. You can see this on the right. And basically it mimics the way a knee bends. And so, yeah, so we've been doing some MATLAB modeling and then sort of looking at the different speed and torque conversions to make sure that it sort of meets our requirements to drive the knee at the appropriate torques and speeds that we need, depending on what obstacle we're at. There's also been talk of potentially doing a mechanism at the ankle as well. I know that part of the mechanical team is doing a little research on that at the moment. So if you're more interested in working at the ankle joint, that is definitely a possibility as well. Although I will say that we're mostly focused at the knee joint for now, because that is the main thing that we're trying to tackle. But yeah. For the electrical team, so basically we're trying to do a lot of sensor integration and sort of just hooking up all of the different components. So this is just a very high level diagram of sort of what we're working with in terms of our sensors and our microcontrollers and our sort of controls with the motor. So basically all this on the top right or top left and left are just different sensors that we're trying to bring into the system that will be read by a microcontroller. And then you have the O drive and the motor over here, which will directly drive the leg. And then we have the NVIDIA Jetson Nano, which is basically just a computer communicating with this microcontroller to basically tell the leg what to do, depending on what the sensor values are. And so on the electrical team, we also do PCB design. So we're actually learning and using Altium Designer. So if you're interested in learning how to do like chip design, basically, or how to incorporate different ICs to do different things, and then doing that in from a point of view of manufacturing, this is definitely a good place to sort of get experience with that as well. And then finally, we do some level of embedded systems. So when you get these ICs and you're working with microcontroller, you have to be able to program the microcontroller to tell it what to do to communicate with these various sensors and O drives and motors and all of that. But yeah.
So this is the picture you saw before of the obstacle course. So as far as controls go, we're faced with this challenge of meeting these several objectives. So like walking upstairs, opening doors, balancing. And we want to transition between these modes easy and seamlessly so we can get the best time possible. This could be automatic, but likely it's probably going to be a manual system where the pilot like selects which mode they want to get the leg in. So we'll have like a separate mode for like walking up the stairs that's configured with a model for that. And one for like going in a straight line and doing these other tasks as well. But at the moment, we're just starting from the basics still. So that's just walking at a constant velocity in a straight line. And from that, we can build up to these other more technically challenging, I guess, exercises that we will have to compete in. Yeah, so conventional prosthetic legs, they use preset angles and parameter tuning. And this is usually has to be controlled by an expert who kind of who tailors the leg to a person's individual anatomy. The main problem with this is it results in a slower, less natural gait with a prosthetic limb. And achieving variable speeds is more difficult through this method, as well as like being able to accomplish these different tasks that we're trying to do. One more thing with that last slide. So you can kind of see there's this cyclical gait pattern. And you can see at the bottom, there's these gait states that you're in, these like color-coded gait states. So that's what we're actually trying to use now is just finding out which point we are in the gait cycle. And can you go to the next slide? So last year, we built some machine learning models predicting knee angle regression based on inertial measurement unit inputs. So that's like velocity and XYZ, gyro, all those sorts of things. And we built models using all those as features and predicted knee angle regression. So right now we're transitioning from exploring this regression model to a classification model, mainly just because it simplifies the task. So instead of figuring out exactly what angle the knee should be in, we'll be figuring out where we are in the state and then how like quickly, for example, we should transition between states. And so I actually have right here, this is the way we control, or we recorded the data for these models that we built that we're using for the machine learning task. So this is a knee brace, and on it you have your IMU right here. So that's connected to your thigh. And then you have this sensor that senses the knee angle bending. So what we did is we had individuals who had two legs. They wore this on their leg, and we kind of just recorded what natural walking would be like. And so one of the challenges with that is obviously we're transferring data from one person to an amputee. So that's another thing we'll have to eventually figure out.
Yeah, so one more aspect of control that we're sort of exploring is this idea of nonlinear control. So walking and then all of these other complex tasks are inherently nonlinear. And so we're trying to sort of figure that out as a possible avenue. I think for now, we'll start with a more linear approach just because it's much simpler and it's a big task to get up to these bigger nonlinear stuff. But possibly in the future, an avenue is not nonlinear. And so a lot of the big robots in industry right now use nonlinear controls. So any of, I believe this is the Atlas, right, Jason? Yeah. That Boston Dynamics has. And then they have a bunch of other robots. I don't know if you guys are familiar with like the dog. I forget all of their names, but they're really cool. So if you're interested in robotics as well, you should look that up. But yeah, so as part of just figuring out controls in general, we've been looking at different simulations as practice for this. So one exercise that the control team has done in the past is figuring out inverted pendulums. And so commonly walking can be modeled as an inverted pendulum as well. So this is just a good exercise to sort of get an understanding of the beginning of what we might have to do for controls. But yeah, I'll show this quick simulation. So the whole idea of inverted pendulum is just swinging it up and then balancing it and then keeping it balanced. But yeah. For like the main software team, so like I said, we're mainly using the NVIDIA Jetson Nano as of now for the main controls of this entire prosthetic. And we're planning on using robot operating system, or ROS, which is like commonly used in any robotic system out in industry, and then sort of organizing the architecture so that there are nodes for each of the core components, and then designing an architecture so that information can be passed through topics to the microcontroller in order to control the O drive and the motor while also bringing in sensor information. So this on the right side is sort of a diagram of the software architecture from a very, very high level. So we have the system dynamics, which is basically the state of the leg. So what state of gait are we in? What is the angle of the knee? Is there any force applied to the leg? I.e., like someone could have a bent knee but be on a stair, so you might sense force throughout the leg. And using that system state X, we can, interpret the information, determine or estimate the state, plan the motion of the leg that we need to do, and then figure out what specific motor control we need to do for that motion. And then, that affects the system dynamics, and then so we sort of just go through that loop over and over again. But yeah, so software team sort of learning ROS, and then sort of starting to piece together that implementation, as well as going through other software exercises to sort of prepare themselves as the other teams are fleshing out their parts. So while the mechanical team is building up the new prototype for the knee, and while the electrical team is sort of building the PCB for the new sensors and other components. But yeah, so I'd say these are like the main tech clusters, not how the teams are organized, but for hardware design, it's going to be a mix of modeling different mechanical systems through SolidWorks or Onshape, whatever you prefer to use or whatever the mechanical team is using at the time. I believe we're trying to shift to Onshape because it has cloud sharing abilities, so it's very good for more cooperative kind of work. 3D printing for prototype design, and then on the more electrical side of hardware, circuit design, PCB design for manufacturing, etc., and then embedded systems along with that. On the software side of things, it's going to be a lot of figuring out how to build an architecture, as well as just learning different software techniques or practices, such as using GitHub for sharing code through different repositories, or even doing simulations for controls through MATLAB and Simulink. And then more specific to the controls, there are like 3 main areas that we're looking at. So linear control, which is a lot simpler. So you have your PID control, your state space models, which are much simpler to do. Your nonlinear controls, which takes a lot more to figure out. So we're not doing that right now, but is an avenue in the future. And then machine learning, as Jacob mentioned before, for like state-based estimation. But yeah, I don't have a slide for the different teams, but I'll just say the 3 main teams right now that we have are the mechanical team. So right now they are working on different prototypes for the knee, and sort of just doing research on the different requirements there. So what torque and speed do we need at various moments of the gait cycle? as well as what different mechanisms can we use to do that conversion of speed and torque depending on the motor that we have. And then also, how do we mimic that 4-bar mechanism design? The second team is the electrical team. And so currently we're trying to do sensor integration. So we have a bunch of different sensors, like a load cell, which measures force, an IMU, which measures orientation, acceleration, etc. An encoder, which measures like the angle for the knee angle. And then we're just trying to put that onto a PCB that can be easily attached to a microcontroller so that we can sort of read those different states. And finally, the last team is software team. And so currently software team, again, is sort of figuring out that software architecture and also just like working with those other various sensors to sort of figure out how to read the data out of them, what type of data they might want to use, how to manipulate that data into something that's usable, or yeah, let's leave it at that. I don't know if Jacob, you wanted to add anything about what software is doing.
No, not really. I think we covered it.
All right, cool. But yeah, so here are some links that you guys should definitely check out. So the next step of joining the team would be to fill out this application. This is sort of to just give us a better idea of what you're interested in, as well as your time commitment, and just a little bit more information that we might need for you guys to get access to the lab, etc. And then also the Discord link on the bottom. We have a Discord. That's where we do all of our meetings online. So meetings currently are Wednesdays 6:30 to 8:30 p.m. and Sundays 4 to 6. And EB3 room 4222. We're currently doing sort of a hybrid, half online, half in person kind of approach, depending on your team. Just because of COVID reasons, we don't want like a huge cluster of people. So, yeah. So like once you guys fill out the applications, we'll sort of review them, and then we'll let you guys know, and sort of we can bring you guys into the lab and show you guys around and sort of help you guys determine what team you guys might want to start on. And you guys can always shift around teams too. So this is not like definite you're on this team. But if you're interested in something, you're welcome to hop around. But yeah, any questions? Oh, go ahead, Jacob.
This application link, if you want to fill it out later, is also on our website, packbionics.com. It's on the homepage if you scroll down to the bottom. But I would recommend getting it done maybe by the end of this week, so that we can look at the applications maybe next week.
Yeah, we'll probably look at it like sometime middle of next week, so that we can get you guys in either that Sunday or the Wednesday after. So, but yeah, we also do have a website, so there's like some more information on there. But yeah, any questions? Anyone have any questions? If not, you guys are good to go. Jacob and I will be sticking around for another 10 minutes or so for you guys, if you guys have any questions. But yeah, go ahead and fill these out. I can also send the application link, forward it.